So here we go. Formula number one, I would describe as the formula to find velocity after a certain time when you know acceleration. So basically velocity from acceleration in time. I would say formula two is how to find a final position for an object that's accelerating when you know acceleration in time. Formula number three is a kinematics formula, which allows you to figure out either an initial or final velocity, knowing acceleration and change in position. The key aspect with that is you do not have time in that formula. So that's one kinematics formula without time. 4 and 5 look pretty weird. So these are ones we haven't seen in class before, but we hopefully understand how to do. So formula 4 is essentially saying displacement is equal to the area of a velocity time graph. That's what an integral is an area. So finding displacement, you could get the area of a velocity time graph. For 5, it's saying the summation or the area of an acceleration time graph tells you the net change in velocity. So kind of similar to number 4. So the change in velocity of an acceleration time graph is equal to the area of that graph. 6 is simply for finding the center of mass of an object. It's a summation of all the masses times their positions in the numerator divided by a summation of all the masses in the denominator. 7 is essentially finding out the effective distance of mass from the center of a round object or a circular object. So it's very similar to what you see in number 6. Here, I don't know why they're choosing to use integrals instead of summations, but they are. So it's essentially the average, basically, location of that mass divided by the total mass of something rotating. 8 is applicable to the chapter we're in now, which is chapter 12. It's essentially helping you figure out how mass is distributed through things. So I believe that symbol lambda on your formula sheet, I looked earlier, and I want to make sure I'm saying this correctly, is linear mass density. So that's one we haven't seen a lot, but it is. It's linear mass density. So it's essentially taking each little piece and multiplying it by the mass per unit piece. So as you can see, it's kind of like an integral-y type thing. 9, you should know. 9 is Newton's second law. Cool. 10 is the formula for the force between two objects. So that's the formula for universal gravitation. 11 is the only formula we have here which involves friction. So force of friction is less than or equal to coefficient of friction times the normal force. 12 is Hooke's law. So that's relating the force on a spring, the spring constant, and the stretch of a spring. 13 is the formula for centripetal acceleration. It gives it to you both in linear terms, v squared over r, and angular terms, which is r times omega, which is angular velocity squared. 14 is telling you that the t, or period of time for something, is equal to 1 over the frequency. So time is in seconds, frequency is in 1 per second, which is called hertz. Those are simply reciprocals of each other. Oftentimes that's for things which oscillate. 15 is the formula for kinetic energy, 1/2 mv squared. 16 is a formula for work, and essentially it's saying that work is the integral or the area of a force versus displacement graph. Again, why sometimes they use r and why sometimes they use x, I don't know, but a force versus displacement graph would equal the work. That kind of makes sense because you've got newtons on one axis, meters on another, newtons times meters, linearly at least, is equal to joules. 17 is the formula that tells you that the change in kinetic energy is equal to the work done on the object. 18 is weird. I probably won't ask this, which is interesting, but so it essentially says the change in potential energy is equal to the area of a force versus basically position graph. So it's a negative of that, And I think I can look at Formula 19 better. I, for the life of me, could not figure out what CF means on that. That means it's a conservative force, so it can't be friction. Friction means mechanical energy is lost. So that's a little weird. So essentially, potential energy is equal to the area of a force versus displacement graph as well. So 19 is something we've talked about, and that's that the force of a potential energy and displacement or position graph is equal to negative of the slope of that graph. So if you have a potential energy versus position with a positive slope, that means your potential energy is increasing, which means your kinetic energy would be decreasing, so you would have a negative force. So that one we've talked about. 20, potential energy of a spring. 21 is what I would call gravitational potential energy in a universal sense, meaning not close to the Earth, not where like G is 9.8 meters per second squared. So it's the potential energy between any two objects. Number 22 is potential energy close to the surface of the Earth or in a constant gravitational field. And notice there it's talking about a delta UG and a delta Y. So it's really change in potential energy. 23 and 24, kind of similar to each other. Power, which is joules per second, otherwise known as watts, is equal to change in energy over change in time. That's an average. So if you basically take final energy minus initial energy over final time minus initial time, you get the average power. To find an instantaneous power, that's formula 24, that would be where you would look at the slope at any instant of a work versus time graph or a change in energy versus time graph. So average is just final minus initial divided by time. Instantaneous is at any instant the slope of that graph. 25 is formula for momentum, linear momentum. 26 says force is equal to the derivative of momentum with respect to time. 27, I would say the easiest way to say this is an impulse equals change in momentum formula. Essentially, impulse is the letter J, it's Newton seconds. It's also the area of a force versus time graph. But I would say that's the impulse formula would be the easiest way to remember that. 28, velocity of the center of mass of an object is basically the summation of all the masses times velocities divided by a summation of all the masses. If you look, it's really similar to formula number 6 for the center of mass of a position, except we're changing positions with velocities. 29 and 30 are things we did earlier when we had the rotational quizzes this year. So angular velocity is equal to change in angular position over time. Angular acceleration is equal to change in angular velocity over time. 31 is the rotational equivalent of Formula 1. Final angular velocity equals initial angular velocity plus angular acceleration times time. Formula 32 is the angular equivalent of Formula 2. Formula 33 is the angular equivalent of Formula 3. So that's kind of nice that they're similar like that in similar order. And so essentially 31 and 32, if you know angular acceleration and time, you can find an angular velocity for 31, an angular position for 32. 33, you don't have time in it, just like you don't have in Formula 3. So that's using angular acceleration and angular displacement in radians to find change in angular velocity. I kind of lied earlier with 29 and 30. Those are basically derivatives to slopes of the graphs for radians versus time and angular velocity versus time. 34 and 35 are the ones where we had that rotational quiz on, I think. So linear velocity equals radius times angular velocity. Remember, units, meters per second equals meters times per second. 35, angular acceleration equals radius times, Linear acceleration or tangential acceleration equals radius times angular acceleration. Meters per second squared equals meters times per second squared. 36 is the general formula for torque. Force perpendicularly acting at a distance, so that x is a cross product, which tells you it's something perpendicular. 37 kind of was described earlier today, saying the total moment of inertia is the summation of all the parts of a system. 38 is another one for moment of inertia. I like the thing that was stated here earlier. It's describing moment of inertia for an object rotating at a certain radius. You could also use the term integral for that to help someone distinguish it between 37 and 38. 39 is a way to figure out the total moment of inertia for something not rotating about the center of mass. So I'm thinking of 39 as something with the parallel axis theorem. So it's the moment of inertia about the center of the mass plus the extra moment of inertia because something's rotating somewhere else. 40, Newton's second law for rotation. 41, rotational kinetic energy. 42 is the work you would do when something is rotating. So that's if you apply a torque over an angular distance. So it's very similar to force times a linear distance. So I would say 42 is work on an object that is rotating. And essentially you're going to be changing the rotational kinetic energy. 43 is formula for angular momentum. 44 is formula for change in angular momentum. And again, you're looking at an area, so it's basically a torque multiplied by a time. Just like how that change in linear momentum we call impulse. I guess you could call this angular impulse, but I've never heard it that way. So the key there is the delta is change in angular momentum. 45 is essentially goes along with 34 and 35. I don't know why they put it down here, but that's change in linear position is equal to the radius times change in angular position. So meters equals meters times 46, again, it's the same thing as 14. I guess they're trying to show you that angular frequency is in there also. That's that lowercase omega. I'm not sure why it's repeated there. They really didn't need to do that. 47, time period for oscillation of a spring. 2 pi radical mass over spring constant. 48, time for period of oscillation of a simple pendulum. 2 pi times the radical length of the pendulum over little g. 49, period of time for oscillation of a physical pendulum. Essentially, that's a little different than number 48 because the mass isn't all located at the bottom. So instead of the length of the whole pendulum, you're looking at the distance to where the center of mass is located. And number 50 is basically figuring things out when they're rotating or oscillating. It's looking at a position with something for a sinusoidal function or simple harmonic motion type function. It's the only one that deals with that. My bet is that I'm hoping that doesn't show up on your test because it's a little bit of a pain because there's a bunch of other ones that kind of relate to that. So that's my description of those. I'm going to stop